Hello, everybody. We'll begin the Networks and Engineering Standing Committee meeting. Thank you all for staying. So we're going to be using the online and the room, and hopefully have a good discussion. So I hope you're all ready to take part. It's been quite a few years since we were all together. It was 2019 in Stuttgart when we last had our in-person meeting, but the truth is we've been meeting every couple of months for the last couple of years. So we've had a lot of Networks and Engineering Standing Committee meetings, and it's been working really well online. We've kept the community together by people who've been sharing their work, and it's been really useful. So we're going to continue this, having the Microsoft Teams meetings regularly, and so do keep turning up for those. I've got some pen and a paper down there. I'm not going to take attendance, but if you don't receive the NESC emails and the invitations to join our online meetings, then please give me your name, email, and institute, and I can add you to our email list, and then you'll be able to join the meetings. So what we wanted to do at this meeting was do something different to what we've been doing online. So I really want to get you all engaged in the discussion of what we're going to talk about. That is, quite simply, what are the challenges that we face? Let's review where we are because we've not been together for some time. What are the challenges facing SLR, LLR? What are the current limitations? So those are the questions that we're going to address, and that could be in the many different aspects or applications of laser ranging. To help us on our way, I've invited a number of speakers to address the meeting, and these are Frank Lemoine to talk about geodesy, Earth observation, Graham Appleby, SLR analysis, geodesy, and station bias. Ivan Prochaska, SLR technology, Julian Chabe about the atmospheric delays that we need to consider, Jan Courde, time transfer, Adrian Burgoyne is going to talk to us about lunar laser ranging, and Michael Steindorfer is going to talk to us about space debris. So there's lots of different areas to cover, but we're going to be focusing on the challenges of those particular areas. So these are some important voices that have agreed to speak to us, but they're not the only voices I want to hear from. So you've heard the question. I want to hear your point of view, perspective. What are the challenges that we need to be considering, and then we'll be making notes and be thinking about these as we plan our future meetings. So be ready with your answer, and we'll make sure hopefully by the end of this meeting everybody will get heard. And that includes all the people that are online. So don't forget, somewhere behind that screen, there's a bunch of people that are also logged in on Teams, and hopefully we're going to hear from some of them as well. But I think I've covered everything, so I'll kick us off because we do have a lot to get through. I do want to just also thank all the speakers for agreeing to do this. I did give them a very sort of open-ended and open to interpretation task, but I'm sure they've all been very happy and very keen. So first we'll start with Frank Lemoine. So Frank, I hope you can hear me, and please, if you're ready, share your screen and tell us what you have to say. Thank you.
Okay, so first of all, thank you, Matt, for the invitation to speak today. So what I'm going to talk about really, I'm going to focus really on the contribution of SLR to altimeter satellite tracking, the determination of mean sea level, and some of the things that we've learned in particular from the meeting that we held last week in Venice. It was our first meeting in-person meeting in 3 years, and there are some pretty incredible results that were presented, and actually some new requirements that are being formulated by the scientific community that I'd like to share with you. So let me start by talking about our flagship satellite right now, which is called officially the Sentinel-6 Michael Freilich satellite. It's a new laboratory for POD metrology on orbit, precise orbit determination metrology. It co-locates 3 types of POD instruments, GNSS, and that includes both GPS and Galileo, with the ability to track those constellations, DORIS and SLR. It includes 2 GNSS antennae and 3 GNSS receivers. And it means with the co-location of these instruments, you can do POD with really unprecedented accuracy. And I'm going to show you some examples of that. And over time, we will gain better handling on all the different sources of error in the altimeter measurement system. And so the challenge is going to be in the future, as I'll explain at the end of the presentation, we're going to have to reduce our error sources even more. So one of the challenges that we face on Sentinel-6 Mike Freilich, as you can see from the shape right here, is that parts of the spacecraft actually have self-shadowing depending on the spacecraft geometry. And this makes the radiation pressure modeling on the satellite extremely challenging, more challenging than on the Jason satellites, which more or less resembled a box, a spacecraft bus, and a wing. And so the approach that we've used in the past, which is what we call this box wing approach, is inadequate. And so there are efforts underway to improve the models. One of them involves a ray tracing model derived by colleagues ESA. There was a presentation by Francesco Gini from the ESA Navigation Office. And there were various other models that have been presented. And so we'll be using those over the next month and year, and we'll be using SLR data to assess whether we can improve the modeling. And the reason we don't want the modeling is because it can map directly into our geodetic products. So what is the GNSS performance that we're seeing on the altimeter satellites? I think there's a presentation in the meeting that discussed this, but let me tell you that, for example, regarding the TRIG receiver that's on Jason 3 and Sentinel-6, that's the receiver that's developed by JPL. It can track, median track length is up to 40 minutes, excuse me. The median phase residual is on the order of 4 millimeters, and the median radial orbit overlap is on the order of 9 millimeters. So that's the precision that the GNSS data is delivering. And we routinely use the SLR data to verify the performance. And so you see a plot on the right from Shayla Desai at JPL, which shows the SLR residuals as a function of elevation. And you can see that the performance of the TRIG receiver on both Jason 3 and Sentinel-6 is comparable. And if you focus on the off nadir angle, which is pointing directly nadir, that gives you a direct measure of the radial orbit error. That is for these GNSS only orbits or GPS only orbits. That the assessment would be that the radial orbit error on the Jason and Sentinel-6 satellites is between 5 and 7 millimeters RMS. So another addition on Sentinel-6 is the ability to track the Galileo constellation, and that's I think that's new for a science mission, and it essentially doubles the amount of data that's available. It doubles the amount of satellites that are available for that provide information, and it means you can do orbit determination either based on the GPS constellation only, the Galileo constellation only, or the two in combination. And again, as Francesco Gini showed last week, you can use SLR data to evaluate the relative benefits of the two constellation types. So we're going to learn a lot by being able to intercompare the performance from these two GNSS systems on the same spacecraft. This, to me, this result actually blows me away. It's quite amazing. We have two POD antennas on the spacecraft. One is the the POD receiver, and the other is the radio occultation or the trig receiver. And it's possible to do a baseline determination between the two and to measure the relative offsets. And so what they found is that these, both Shailin Desai and his group at JPL and Olivier Montenbroek and his group at DLR, that there's an offset of plus or minus 9 millimeters in the location of the POD receiver and plus 5 millimeters in location of the trig receiver. And that's consistent with an offset in the assumed attitude of the spacecraft as provided by the star tracker data or the quaternions of 0.43 degrees. And the problem with that misalignment is that it produces spurious accelerations in the orbit modeling. So this is the level of precision in POD that we're actually operating with. So what is the current level of performance that we have on the current set of reference missions? When I say reference missions, these are the missions that are used to produce the index of the rate of change in global mean sea level. So it's the JSON satellites and Sentinel-6A right now. So we do this assessment in two different ways. One is to intercompare orbits from different analysis centers, in this case, JPL, NASA Goddard, and the CNESC. And we find that over the JSON missions, in terms of radial performance, JSON-1, the orbits agree between 8 and 10 millimeters. On JSON-2, between 6 and 8 millimeters. And JSON-3 and Sentinel-6 between 5 and 7 millimeters. And again, you can map out the performance for both satellites as a function of elevation angle, and you can see the varying performance of the different orbit solutions as a function of elevation. But the point I want to stress here is that there is a floor in performance, and it's on the order of 5 millimeters. And that's probably the floor right now of the performance of the SLR systems. And so given the performance of GNSS right now and how it's likely to continue to improve for various reasons, I think the challenge for SLR is you want to move this floor further down. You want to move your performance more towards a system where you're getting millimeter level performance and where the biases aren't contaminating your ability to do absolute error calibration. So now I'm going to talk about what is the future evolution of the altimeter satellite constellation. I'm not going to give you a complete inventory because that would be very boring, but I'm just going to talk about what is considered to be the operational ocean radar altimeter satellite constellation. And it's basically the satellites that will be operated by under the auspices of the Copernicus program by EUMETSAT. And so it includes the reference mission satellites that I mentioned, Sentinel-6A. There will be successor missions that will be launched in 2025 and 2030. There's the Sentinel-3A and 3B missions, which are polar orbiting radar ocean altimeter satellites. And there will be successor missions launched in 2025 and 2027. And you heard about the Cristal mission from Jaime, which will be launched later in this decade and early in the next decade. I would point out that the plan is for all these missions to have tandem flight modes for intermission instrument calibration. It's essentially a mission requirement. So the measurement of global mean sea level, as you're all aware, is a key indicator of climate change. And now we have a time series that's long enough that we can actually determine the acceleration. These are the latest values from this particular time series presented by Brian Beckley last week. And so we can make a data-driven assessment of what will be the near-term impact on coastal communities. And in addition, you can actually use data to make an assessment, hopefully in the near future, as to what climate trajectory we're following. So that's one of the goals of this measurement. So one of the interesting developments at the meeting last week was the improvements that are being advocated in the scientific requirements for altimeter measurements. And this was presented by Bruno Messignac of the CNESC. And so one of the goals is to better measure the global mean sea level, because the global mean sea level is a key component to closing the sea level budget. And by closing the sea level budget, that means taking the altimeter height that's measured from altimetry and combining it with the height that's determined from in situ measurements that are determined by temperature, a global fleet of floaters called Argo that measure temperature and salinity, and comparing and then subtracting off the mass contribution from GRACE. And being able to do that closure of the sea level budget also gives you a handle or an ability to measure the Earth's energy imbalance. And so how much is the Earth heating up? And so Messignac from the CNESC argues that we should be, instead of only making that measurement using satellites that make radiance measurements, it's also accessible through satellite geodesy. But it means that the error in the global mean sea level trend has to be reduced from 0.4 millimeters per year to 0.1 millimeters per year. And it means all the components of error in the altimeter measurement system. And so it might include high frequency errors, wet troposphere correction instabilities, the ITRF, the GIA, orbit error, all those would need to be reduced. So that's going to be the challenge in the future. So my message to you, I should also say that this is proposed by the scientists of the Copernicus Climate Service, but it will likely be adopted in future missions that fly in the next decade. But the implications for all the measurement systems certainly haven't been mapped out. But don't expect any relaxation of the GGOS requirements for the reference frame. And my message is keep working to develop SLR systems that are stable at the millimeter level with minimal biases over the long term. That would be my message. Thank you. Oh, and there are topics that I've not talked about, which might also, that you should know about, and that is that SLR, satellite laser ranging, also contributes to mass estimation from GRACE follow-on. In fact, as some of you are aware, the C20 and C30s on GRACE follow-on from the GRACE data are not reliable, due primarily to issues with the accelerometers. And so they rely on the tracking of the geodetic satellite constellation to determine those for estimates of mass change. And then, of course, there's the whole issue of geocenter. The degree 1 component of mass change is not observable from GRACE. And so that has to be provided either by a model or through an external geophysical solution. And then the final issue is that the error in the GM of the Earth, which is the scale of the reference frame, maybe this is a matter of debate, but it's probably on the order of 1 ppb, and that's larger than GGOS requirements. So that's my summary. If there are any questions, I'd be happy to answer them.
Thank you, Frank. That was really powerful and really up to date and the latest information and relevant. And so it was really a good message for us to hear. Would anyone like to ask a question or make a comment at this stage? Tom, yeah.
So if the GNSS receivers are having radial errors of say 5 to 6 millimeter, and if the current SLR performance is at that level, so we are not really adding anything to improving the accuracy of the orbit. Rather, we are far away from it. So when do you think we can get to the 1 millimeter level so that we can make an impact on such satellites?
Is that a question for me?
Yes.
Well, I mean, hopefully the development of the next generation systems will contribute to that. But as you saw in Van's presentation earlier today, there are a lot of components that contribute to potential errors at the level of a millimeter. And so it's going to take a lot of technical work to make sure that the stations can operate in a reliable manner and deliver millimeter level geodesy. I think, I think you have to be honest. The GNSS systems are very powerful. There's a lot of investment that's being made, technical advances that are being made, and it's really important for SLR to continue to evolve and to move towards systems that have higher precision and higher accuracy.
Great, thank you, Frank. Thank you very much. And taking that message of that we need to reduce our SLR error source